Hello and welcome back. Today we're going to introduce the inverse function and what its relationship is with its derivative. Well, let me actually start with explaining what an inverse function is. So for example, let's denote the following function. F of x equals y, in which there's a certain input right here, and then there's a certain output right here. Okay. So pretty much an inverse function sounds exactly like what it says. In a normal function, we have an input and we get an output. You go that way. So pretty much an inverse function will go the opposite way. You're given an input and you want to get the you're given the output and you want to find what the input is. So what I mean, I'll write the following notation to symbolize that it's an inverse function of the output, and it'll give me the input. In other words, the inverse function uses the output to give you a certain input. So so in a normal function, you put in something and you get something out. You put what you got out into the inverse function, you got what you put in. So let's actually use some manipulations for this. So here we see an x, right? And you also see an x right here. So let's actually substitute it back in. So we have an f, we have an x right here. We're going to substitute this because this is equivalent with x. Inverse of y, and this equals y. Okay, interesting. And let's do it the other way around. So here we have a y, and we're going to substitute it with this y. So f of -1, and we go y equals f of x. And the inverse function is equal to x. Okay, so we see in a way how the inverse function and the function outdo each other. So pretty much it's like if they cancel themselves out to obtain y equals y, and if they cancel themselves to get x equals x. In other words, the following notation is true. Whatever I put in here, for example, I can put an x, you'll get an x out. I can put a y, and you'll get a y out. Same thing the other way around. These are, in a way, composite functions. So, once we took that into account, let's actually do something with it. We know how they outdo each other, like I've just shown, but let's actually take the derivative. Because in this video we're interested in how the derivative of the inverse function relates with the derivative of the normal function. So, we have, let's denote f of x as the normal function, and let's denote g of x as the inverse function. Okay? So pretty much normal function, inverse function. Let's actually take a composite idea of it, like we did before, right here. We took a composite of the inverse and normal function to get an x. So let's actually do the same thing. We're going to take f of g of x equals x. Please take into account that this is the normal function, this is the input function, and like I've just shown, they outdo each other, and you get x. Okay, if you understood it to that point, let's actually take the derivative. Remember, this is a composite function, a function inside a function. If you take the derivative of that, what is it? Well, if you remember correctly, that is actually the chain rule, in which states it's the derivative of the outside, okay, f of prime. Keep the inside the same, and then the derivative of the outside. Of the inside, my bad. So, we kept the outside, we took the derivative of the outside, kept the inside the same, and then we took the derivative of the inside. And also take the derivative of both sides. Derivative of x is just 1. Okay, and we want to isolate what the inverse derivative is, because this is inverse, g of x. And we get into account that g prime of x equals 1 over f prime of g of x. Okay, great. We've actually shown what the derivative of the inverse function is. And now this is very important because let's say we wanted to find the derivative of functions such as the inverse of sine. For example, we have sine of x. If we take the derivative of that, we get cos of x. Okay, good. But how about the inverse of sine of x, or in other words, the arcsine of x? What's the derivative of that? Well, we have two options. We can use the following formula we've derived for any function, as long as it's bounded and it has an inverse function. Or we can take it the intuitive way. In other words, an inverse function tells us you put in an output and it'll give you an input. So in other words, let's denote y as the output, alright, and it'll give us an input. This is the same thing as writing arcsine, okay? And let's actually take the derivative of this. So, this is respect to x. So the derivative of the inside is just dy dx. Take the derivative of the outside, which is just cosine of y. And this equals to the derivative of x is 1. We're interested in finding what dy dx is. So isolate it. Dy dx equals 1 over cosine of y. Alright? Now, you might think we're done here, but not exactly. It's very inconvenient to leave it like this. We want to write it in a way like we had it before, dealing with x's. So, in order to rewrite what we have in the denominator right here, we're going to have to somehow write it in a way in which it includes a sine of y, so we can replace the y's with x's. So let's actually do that. How can I write cosine of y in order to include sine of y? Well, if we look at the definition of a simple property, sine squared of x plus cosine squared of x equals 1. Alright, now if we isolate it for cosine of x equals 1 minus sine squared x, and we have to take the derivative. Cosine of x equals the derivative, not the derivative, the square root, my bad, the square root of 1 minus sine squared x. Alright, you see how here there's also a cosine, just with a different variable? Well, we can actually do the same thing. We can just rewrite as dy dx equals 1 over square root 1 minus sine squared x. And in this case, y. We're dealing with y's. You can replace everything here with y. So, right here we have a sine of y, right here. Also there. And we know that sine of y is equal to x. But here we have sine of y squared. So that is just simply dy dx equals 1 over square root 1 minus x squared. So, the derivative of arcsine of x, which we were initially interested in, results in simply 1 over square root of 1 minus x squared. Now this is very amazing. It's an amazing fact because here we have the trig function, and you're probably thinking, whoa, trig functions have nothing to do with algebraic functions, and just using that idea, its derivative is actually just simple algebraic function. Well, let's actually go into its analyze their cousins. For example, the inverse, the arctan of x. How do we find that? Well, let's have the same idea. This can be rewritten as tan of y equals x, because this is the inverse right here. It's saying you're putting an output, which is y, and you're getting an input. So, using that idea, we can just simply take the implicit differentiation of both sides and get dy dx. Derivative of tan y is just 1 over cosine squared of y equals 1. Okay, simplify, or in other words, isolate dy dx, and you get cosine squared y. Okay, now we have the same idea. You might want to leave it like this, but you'll have a problem. You want to write it in a way in which we had the x, so you can have an input, because in most problems you want to find the derivative, you want to put the input, not the output. So, how can we rewrite cosine squared y in order to write it in terms of tan of y? Well, let's go back to our simple formula. Sine squared y plus cosine squared y equals 1. Okay. What happens if I actually divide everything by cosine squared of y? Well, this will turn to tan squared y. This side will turn to 1. Cosine squared of y divided by cosine squared of y is 1. And in this side, it will turn to 1 over cosine squared y. Well, you see, right here we have a cosine squared y, and here we have a cosine squared y. Let's find the, let's take the reciprocal of both sides, of this side and this side. We get cosine squared y equals, and here, the reciprocal is just tan squared y plus 1. Well, there you have it. We can just substitute this with this, because it's in terms of simple tan squared y. So, dy dx now equals 1 over tan squared y plus 1, and tan y is just x. So right here, this is just x squared. dy dx equals 1 over x squared plus 1. Wow. Another amazing fact. The derivative of a trigonometric function actually gives us an algebraic function. Very unexpected. And for our last cousin of the trigonometric series is going to be sec, or in other words secant. So remember, sec of x is the same thing as writing 1 over cosine of x. Okay? So sec of x equivalent to 1 over cosine squared x. We're going to find the derivative of the arcsecant of x. Alright? So we can have the same idea. We're going to rewrite sec. Sec of y is equivalent to x. We're having an output and we're getting an input. Alright? So then we can just take the derivative. dy dx. Okay? Now we're going to have to take the derivative of sec of y. Sec can be rewritten as 1 over cosine of y. Right? And 1 over cosine of y can be rewritten as cosine of y. Now we're doing this because it's more convenient to take the derivative. Cosine y to the negative 1 power is the same thing as this, which is the same thing as sec y. Let's actually take the derivative of this, which is a simple one. Negative 1 cosine y negative 2. Then the derivative of the inside, which is simply negative sine y. Cancels out. We're left with sine y divided by cosine y squared. So the derivative, now we can just write it right here, which is just sine y cosine squared y equivalent to 1. We took the derivative of both sides. This sine y divided by cosine squared y is just simply the derivative of secant y. Let's isolate dy dx like we've done in previous videos. Dy dx equivalent to cosine squared y divided by sine y. Okay, well, we're in the same problem. We want everything rewritten in terms of sec of y. But in this case, it's a little bit more complicated. We have two different functions. How are we going to do this? Well, I asked myself, sec of y is the same thing as 1 over cosine of y, right? Okay, here we have a cosine of y. Is there any way we can actually change it? Well, let's first split it, because it's squared. It's the same thing as cosine y times cosine y, right? And I did that because I can do the following. I can bring down this cosine of y down, so dy dx. I'm not doing any changes, I'm just rewriting it. 1 over cosine y. Now, if you notice, this is a simple algebraic manipulation. I can write it as 1 over cosine of y because this is simply just cosine of y. So, but this, I did it like that because here I find that this is equivalent to x. So, grabbing another paper, we're going to finish the substitution. Dy dx is equivalent to cosine of y. Remember, we rewrote it like this so we can substitute it with x because this is now secant of y. So, upon getting secant of y, we can replace it with x, and then here we have sine y. We're almost done, but not there yet. Remember, we want to find a way which we can write this whole statement of terms of secant of y. Well, how can we rewrite sine of y in a way get closer to cosine of y? Same idea. Dy dx equals, let's leave the cosine y up there. Here we have an x. Sine of y is the same thing as square root 1 minus cosine squared y. Alright, getting close, getting close. But what else can we do here? It's not exactly secant. We can actually do the same idea. Let's actually bring this down as 1 over cosine y. Dy dx equals 1 over x 1 over cosine y times square root 1 minus cosine squared y. Now we're almost done here. This is a very important part. We want to rewrite things in a way so we can have secant. Now I immediately see here that we can actually multiply this inside. Now it's pretty much like doing the opposite of getting stuff out of square root. So what I mean, I'll give it a small example. We have, for example, 4 minus x squared, and I want to simplify this by having a 1 here. I'll divide this whole inside statement by 4. So I'll simply get 1 minus x squared over 4, right? And we just take the square root of 4 because it's alone, and we get 2. Like that. Now pretty much what I'm going to do here I'm going to do the opposite. Instead of taking stuff outside, I want to bring the 2 back inside. So I do the opposite operation. I square it, because I'm introducing it back to a square root. So I square it to get 4, then I multiply times the statements inside. So here, 1 over cosine y, let me square it. So now it's over here. Cosine squared y times 1 minus cosine squared y. Well, let's actually reintroduce into the statement. 1 over cosine y times 1. Oh, I see a secant already. Cosine y. And cosine squared y divides the cosine squared y right here. So that just leaves minus 1. Okay, we're almost done. Here we have a secant. Now it's just terms of rewriting it. So we have dy dx equals 1 over x. And right here we have 1 over cosine squared y, which is just secant squared. So now we can write as x squared minus 1. Wow, this is very profound. The derivative of an inverse secant function is actually another algebraic system. So actually they're very interrelated. But till next time, hopefully you've enjoyed this and it may help you in your calculus journey. Thanks.